Namaste and welcome to yet another video from Murali's World of Physics. In my last two videos, I had elaborated on the game of Carroms, the board on which the game is played, and some physics concepts and principles and laws involved in this game. In this present video, which forms the sequel to the previous two videos, I propose to elaborate on a mathematical formulation of the basic physics principles and laws involved in the game of Carroms and the Carrom board. In a nutshell, the main physics concepts that we discussed earlier are the following: forces, velocity and acceleration, kinetic energy, linear momentum, and collisions between objects. The main physics principles and laws discussed so far were Newton's law of universal gravitation, Newton's laws of motion, and the conservation laws of momentum and energy. Of these, the laws of motion and the conservation laws are most important as far as the game is concerned. We will apply these laws to the main physical process involved in the game, namely collisions. We recognize different classes of collisions on the Carrom board. Firstly, we have the striker coin collisions. When the player strikes a coin with the striker, it results in collisions between the striker and the coin. These collisions determine the initial motion and direction of the struck coin. Secondly, we have the collisions between coins. When two Carrom coins collide with each other during the gameplay, these collisions can be elastic or inelastic, depending on the various characteristics of the materials of which the board, coins, and striker are made. Thirdly, we have coin board collisions. When a coin hits the edges or pockets of the Carrom board, it experiences collisions with the board. Obviously, this happens only if the coin had been hit by the striker or another moving coin. Finally, we have the striker board collisions. These can also be called rebound collisions. The idea here is to hit a coin indirectly in the cases where the coin cannot be hit directly by the striker, or the coin may be obstructed by another coin for a direct shot. As discussed in our earlier video, collisions can be either elastic or inelastic. The difference lies in whether the total kinetic energy is conserved. In this case, the collision is elastic, or kinetic energy is not conserved. In this case, the collision will be inelastic. One important concept that one should have prior to playing the game of Carroms is that of angles. These angles are those formed between some pairs of imaginary lines on the board. Such lines are the trajectories of the striker and the coins, and the lines joining the edges of the board. All these lines are essentially straight lines. The trajectory of the striker is a straight line starting from the center of the striker to the point of contact with the coin or the edge of the board. The trajectory of a coin is a straight line starting from the center of the coin at its current location on the board to either one of the corner holes or towards the edge of the board. So here the trajectories are shown on the board. So here the various trajectories are shown. The red lines 1, 2 and 3. So this 1, 2 and 3. These are the striker trajectories. And the blue ones 1, 2 and 3 are the coin trajectories. Now here 1 and 3 are direct or straight shots, and that 2 is an oblique shot. Another critical aspect of Carrom shots is understanding the principle of reflection. When the striker hits the board edge, it bounces off at an angle equal to the angle of incidence. When the striker hits a coin, it bounces off at an angle equal to the angle of incidence. So this follows the law of reflection, a fundamental principle in physics, namely optics. For striker rebound, so we have the striker being struck, and it hits the board directly and it rebounds from the opposite edge and then hits a coin. So here the law of reflection gives the angle of incidence theta I is equal to the angle of reflection theta R. This is basically for elastic collisions. For inelastic collisions, this will not be true. Similarly for coin board collisions. So if a coin has been struck by the striker and it goes towards the board edge and then rebounds. So there also, in the case of elastic collisions, the angle of incidence would be equal to the angle of reflection. Then we have the striker coin collisions. So this is a schematic of a typical striker coin collision. So here P prime, the line P prime is the trajectory of the center of the striker, and IO is the trajectory of the edge of the striker which hits the edge of the coin. So this edge of the striker hits the edge of the coin here. Then OR, so this is the OR, the trajectory of the striker edge after collision. Then ON prime is the trajectory of the coin center after collision towards the pocket. Why towards the pocket? Because it is the aim always of the player to pocket the coin. So therefore, he would like to have the trajectory of the coin after being struck by the striker to be towards one of the four pockets. Similarly, TT prime is the common tangent at point of contact O. So this is the common tangent at the point of contact. And NN prime is the normal to the tangent TT prime. The angles are now indicated in the diagram. So these angles are measured relative to the common tangent or the normal to it. So we either measure the angles relative to TT prime or with respect to OL. So ION is the angle of incidence of the striker. NOR is the angle of reflection or rebound of the striker. ION prime, which is phi, is the angular reflection of the coin. And IOT prime, this is equal to 90 degrees minus the incidence angle, and this is known as the normal angle. The normal angle is the angle formed between the line of impact, that means the path of the striker, and the line perpendicular to the direction of the coin you aim to pocket. Now, it happens that by striking the striker at a normal angle, the chances of pocketing the coins are high. This is because the striker imparts a force on the target coin, transferring its momentum and directing it towards the particular pocket at which we are aiming. In such collisions, the force exerted on each circular disc will be along the line joining the centers of the two discs, hence normal to the common tangent TT prime. Now let us suppose that the velocity of the striker is US along IO before hitting the coin and Vs along OR after rebounding. Vc is the velocity of the coin along ON prime after being struck by the coin. Of course, before being struck by the striker, we assume that the coin is at rest. So we are concerned only with the velocity of the coin after it is struck by the striker. So Vc is that particular velocity. Now all these have been indicated in the earlier diagram. Now applying the law of conservation of momentum components along OT and ON, we have ms us sine theta I, that is a component of the momentum in one direction, that is equal to ms vs sine theta r. Similarly, ms vs cos theta I should be equal to ms vs cos theta r minus mc vc. So these are along two perpendicular directions, the momentum components. So according to the law of conservation of momentum, the respective momentum components should be equal before and after the collision. So now if we apply the law of conservation of kinetic energy, we have ms us square by 2, that is initial kinetic energy. Only the striker is in motion before the collision, so we have only the kinetic energy of the striker of ms us square. And after the collision, both the striker and the coin are moving with velocities vs and vc. So therefore the combined total kinetic energy is equal to half ms vs square plus half mc vc square. So the principle of conservation of kinetic energy tells us that these two should be equal. By solving the above equations, one can extract expressions for the unknown angles and velocities after the collision. In order to pocket the coin, its direction should be along the O(n) prime direction. In the context of collisions on the Carrom board, we therefore know definitely the orientation or angle of the final trajectory of the coin. Thus, it may be easier if we take our reference as the line O(n) prime. We will consider the angles with reference to this line. Squaring both sides of the momentum equations and adding these up, one can eliminate either theta I or theta r, and then utilizing the energy conservation equation, obtain an expression for these angles. So if we do this exercise, we will get the final results that cos theta I is equal to mc plus ms into vc by 2 ms us, and cos theta r is equal to mc minus ms into vc by 2 ms vs. Now consider frictional force between the striker and the board, that is mu s msg, where mu s is the coefficient of friction between the striker and the Carrom board surface, and that between the coin and the board, which is equal to mu c mcg, where mu c is the corresponding coefficient of friction between the coin and the surface of the board. The effect of these forces is obviously to retard the striker and the coins. We now assume that the velocities in our equations are those at and immediately following the actual collision. Therefore, the actual velocity of the striker at start will be more than us, and that of the coin when it reaches the pocket will be smaller than vc because of the action of these retarding frictional forces. Let us put some numerical values into our equations. Let the mass of the striker be ms is equal to 15 grams and that of the coins be mc is equal to 5 grams. These are typical masses of the striker and the coin respectively. Also typical coefficients of friction are mu s is equal to 0.2 and mu c is equal to 0. Let's say we take the distances IO is equal to 54.4 centimeter and O(n) prime is equal to 30.6 centimeter. Some typical values. The retarding frictional force on the striker is mu s ms g is equal to 0.2 into 0.015 into 9.8, that is equal to 0.0294 newtons. For the coin, this value is mu c mc g is equal to 0.3 into 0.005 into 9.8, that is equal to 0.091 newton. When the coin reaches the pocket, its speed should be greater than 0, because otherwise, so the coin has to reach the pocket. So that means at that point, its velocity should be slightly greater than 0, so that it can overshoot the edge of the hole and fall into the hole. Therefore, using the kinematical relation v square is equal to u square plus 2as, with v is equal to 0, u is equal to vc, and a is equal to minus mu cg, and s is equal to 0.306 meters. We have 0 less than vc square minus 2 mu cg into 0.306. Therefore, we get vc should be greater than square root of 2 mu cg into 0.306. Now we take the minimum value of 1.34 meter per second from this equation. Now from expressions for cos theta I, which is given earlier, this should be less than or equal to 1 obviously. Therefore, Vc by Us should be less than 2 ms by mc plus ms, that means less than or equal to 1.5. So let us take Us is equal to Vc by 1.5, is equal to 1.34 by 1.5, that is equal to 0.88 meters per second. So this is the velocity of the striker at the time of collision at A. The starting velocity at I can be calculated by accounting for friction. So this gives a value of 0.91 meter per second. In order to pocket the coin as shown in the figure, we know definitely the lines IO and ON prime. So IO and ON prime, these are known because we place the striker at a known position and the final destination point of the coin is also known. So therefore, the current location of the coin also is known. So therefore, these two lines are well defined. Hence, the angles made by these directions with our x and y axes are known as indicated. So we have x and y axis, and the angles, corresponding angles are shown here. A similar analysis can be carried out for coin-coin collisions also. The striker and coin rebound shots from the edges of the board are also important. So like this, striker hits the edge of the board, rebounds and hits a coin. Then this has to be pocketed. So this is a indirect shot. Now also one can have a direct shot in which the striker hits the coin, it goes and rebounds from the opposite edge and then it is pocketed. So these types of rebound shots also are important from the point of view of the Carrom game. Here we will wind up our discussion on the mathematics of the game of Carroms. Thanks for watching this video. With this is Professor Muralidhara Warrior signing off from Murali's World of Physics. I'll be back with more interesting videos on physics concepts and principles. Till then, goodbye. If you like this video, kindly click on the like button and share this video with your friends and relatives and in your different groups. If you have not already subscribed to my channel, kindly do it now. And please don't forget to click on the bell icon so that you will get notifications in future regarding my upcoming videos.